When you were growing up, what kind of toys did you wish for? Perhaps an autonomous AI-driven turret was on your Christmas list. Well, I built one. My excuse for building it was nature decided to send a chemical weapon to my backyard. But how do you actually build a machine that hunts? You give it an anatomy. You let it see through a webcam. You let a Raspberry Pi 4 act as its brain. You let a Raspberry Pi Pico act as its reflexes. And you give it stepper motors to act as its muscles. So here's how I built it. I started with a skeletal frame. I got the basic movement down first. I wired the stepper motors to the motor drivers, which are necessary to control and provide the 12-volt power the motors need, and wired those to the Raspberry Pico, which would control the logic behind how much power the motors got and in which direction. After some tinkering, it moved up, down, left, right, the basics. The next item on my agenda was to make it think. But how do you teach a machine what a skunk looks like? In order to train a model, I needed a database. So I made one. I downloaded roughly 100 images of skunks in different positions, from different angles, in different lighting, and you might think that's the tedious part. But you'd be wrong. See, when you train a computer vision model, you have to give it an image and a structured text box showing the numerical coordinates of the bounding box where the desired object lies on the image. After gathering each image, I had to manually label each skunk in each image inside Label Studio, drawing a precise bounding box over every tail, stripe, and silhouette. Another quirk I learned was to purposely leave around 5% of those images completely empty. In machine learning, injecting these blank background images prevents the neural network from hallucinating objects or throwing false positives when there's nothing there. I fine-tuned a light YOLO object detection model and tested it. On my PC, it ran at a smooth 30 frames per second. It was flawless. Then I migrated the model to the Raspberry Pi 4. 0.5 frames per second. A flawless slideshow. If a skunk walked past the camera, the Pi wouldn't realize it, effectively making the skunk seem like it was teleporting. So I optimized. First, I implemented post-training model quantization, shrinking the model weights down to an optimized format to help ease the computation strain on the CPU. Second, I introduced multi-threading. Think of multi-threading as multitasking. Your left hand scrolls on your phone while your right brings your fork to your mouth. By isolating the frame capture process into its own dedicated I/O thread, I ensured the camera could buffer frames independently without getting bottlenecked by the heavy computer vision inference loop. The result was 2 frames per second. To a PC gamer, that is an absolute travesty. To me, that is a 400% performance increase. I finally had a functioning brain. Ish. But by introducing multi-threading, I also introduced a completely new nightmare: thread locking. Because the video pipeline and the physical hardware loops were running in parallel, they constantly fought over the same shared variables. The real battle was preventing race conditions. To keep the turret responsive, I structured the software around 3 pillars. 2 background threads running alongside a custom local Flask web server. Thread 1 handles the heavy computer vision and state logic. Thread 2 runs the high-frequency hardware output loop entirely in parallel. Because these layers run concurrently, they still constantly fight over the exact same variables. If the main automation thread tried to update the target coordinates at the exact millisecond my web-based manual override tried to zero out the system, it would cause a race condition, freezing the entire turret. To fix this, I wrapped the coordinate variables in a strict threading lock. Think of it as a digital game of hot potato. Only the thread currently holding the potato, the lock, is allowed to read or write the coordinate data, completely eliminating the risk of a collision. When a manual override occurs, the script instantly acquires this lock and intercepts the automation. It completely drops the automated search, sweeping, and alignment flags, forcing the target registers to mirror the manual position. If there are no manual inputs, the system releases this lock and resumes its automation. Once safe, It packages the payload into a clean string containing X and Y coordinates, a fire indicator, and an error code byte. This payload is encoded into UTF-8 and blasted out over the USB serial port to the pico every 20 milliseconds. The Raspberry Pi Pico catches those data packets, translates them into step pulses, and fires them directly into the stepper motor drivers. This infrastructure feeds a state machine with 5 core behaviors: manual, search, locked, predicting, and sweeping. In manual, it receives the movements from the user via web application. In search, the turret sits idle until detection occurs. Locked means a target is found, and the turret has successfully positioned it in the center of the crosshair. If a target was found and then lost, it falls into a predictive state, tracking where the target should be based on its last known velocity, before giving up and resetting to the center position after 5 seconds. And sweeping, which moves the turret on its x-axis to scan the surroundings in a 60-degree pan. Because I didn't add physical limit switches, I coded a digital bounce protection layer, capping the physical angles to a 180-degree window horizontally and a 90-degree window vertically to protect the internal wiring from twisting apart. Which brings us to the ultimate question. What about firing? It is a turret after all. Before firing, the turret has to find the target. Because the camera is mounted on the turret head, wherever the turret turns, the camera sees. Meaning, to hit something, it has to be looking at it. The distance from the center, looking at it, and the object is called the error. When a skunk enters the frame, the state machine hits search mode. The system calculates the error and applies a proportional derivative loop. A fancy way of saying it calculates how far off-center the object is, how fast it moves, and adjusts the turret head while gracefully slowing down to avoid overshooting. Once the target error drops below a pixel alignment tolerance, a lock-engaged flag fires. The Pi 4 flashes a fire signal to the Pico, which instantly shoots a voltage pulse to an internal electronic switch, closing the circuit and triggering the motorized water gun mounted to the chassis. At that exact millisecond of alignment, a rate-limited image capture function runs, logging a time-stamped image into a local directory on the Pi storage. But leaving all this data and control unlocked isn't ideal. I didn't want anyone else logging into the device and controlling the turret manually. To secure the control dashboard, I added an authentication layer to the web server. If a browser tries to access the controls without a valid security token, proving it's me, the server slams the door and redirects the user back to a secure login page. With the software locked down, I finally felt confident enough to put the machine to work. I left the turret out all night. It sat in the dark, running its loops, processing 2 frames every second, just waiting. The next morning, I woke up like it was Christmas. I checked the logs. The system fired 14 times, 14 separate detections. 13 of them were false positives, caused by a shadow, a chair arm, or a change in morning lighting. The machine aggressively water-gunned the fence. But the 14th photo was an incredibly blurry, chaotic, low-light night photo of a skunk running away. The code worked, the hardware worked, and I felt awesome. Now, in all seriousness, it was probably the loud grinding sound of the stepper motors that actually ended up scaring the animal away. But for all intents and purposes, that still works. So where does that leave us today? Well, when I get enough data and enough images, I aim to retrain the model so it stops shooting my own fence, and further optimize the code so it runs faster, ideally getting as close to real-time tracking as I can. Looking back on this project, I've learned an absolute ton. I got my hands dirty and actually built something physical. It literally exists, and it works because I programmed it. Through the entire process, I walked away with invaluable lessons, some personal, some technical, and some that apply to life as a whole. I enjoyed making this project so much that I gave it a name. If there's one major takeaway that I can pass on, it is simply this: go build something. Go build something. You will learn far more that way than any other, because it's through the failures and the frustration that you truly expand. But if you don't feel quite ready to jump into your own projects and want some more inspiration, I know just the video for you.